So today we're going to talk about how you actually compute determinants. So let's recall what we did last time. We characterized the determinant in terms of three properties. The exchange property. If you exchange any two rows, the determinant changes sign. And the linear property, the function is linear in each row. And the normalization that the determinant of the identity is 1. Now, before we go on and state some formulas, I wanted to do one example. This is the Vandermonde determinant. I did this briefly at the end of class last time, but I want to say it a little more carefully. So suppose we have n variables x1 through xn, and we make this big matrix which has the various powers of the xi's in it like this. You put the powers of x2 in the second column and so on, and the powers of xn in the last column. And this is an n by n matrix, and I'm interested in its determinant. Well, if you write out its determinant, it's clearly some polynomial expression in these variables, x1 through xn. And notice that what happens if xi is equal to xj? So for example, suppose x1 was equal to x2. Well, this second column here, if x2 is equal to x1, you would get this, and that's exactly the same thing as the first column. So by the basic property, if you would have two columns are the same, and we know that that implies that the determinant is 0. And by properties of polynomials, that means that this determinant function has a factor of xi minus xj. Because when you set xi equal to xj, you get 0. And this little argument actually proves the following fact. The determinant of the Vandermonde matrix is the product of all these terms, xi minus xj, for as I runs over less than j. So, for example, x1 minus 2, x1 minus 3, x1 minus n, x2 minus 3, and so on. All of these terms. So let's look at an example. Take n is equal to 3. And here's the 3 by 3 Vandermonde matrix. And what I'm saying is, well, if you compute this using the usual formula, you get this rather complicated thing. And what I'm saying is that this is actually equal to this much simpler expression, x1 minus 2, x1 minus 3, x2 minus x3. And if you don't believe me, multiply this out and you'll see that these two things are equal. And the whole point here is that this is obviously a much nicer formula, and it's in fact much easier to prove. And what this illustrates is that sometimes it's important to think instead of just applying formulas. But anyway, sometimes you do just need to know the formulas. So let's look at a few formulas that we can use. So I've already talked about one of these in class, which is the permuted Ldu or Ldu decomposition, actually. So you can write any matrix as PA is equal to LDU, where P is a permutation matrix, and as usual, L is lower triangular, U is upper triangular with ones on the diagonal, and D is a diagonal matrix. And by the product formula, of course, that says that the determinant of A is plus or minus 1 times the product of these diagonal guys, where the plus or minus 1 is the determinant of the permutation matrix. And we've seen that that's always plus or minus 1, and it's minus 1 to the number of swaps that you need to get it back to the identity. And we saw in class that this formula is handed to you by the various properties of the determinant. So we're going to use this sign a lot, and so let me introduce a little bit of terminology. If you have a permutation of n objects, the sign of that permutation is the determinant of the corresponding permutation matrix. And so, for example, if you have the permutation which exchanges 1 and 2, the corresponding matrix is this matrix, and the sign of the permutation is therefore -1. So the sign of a permutation is just another word for the determinant of the permutation matrix. And with this terminology, the formula is the determinant of A is the sign of the permutation times the product of the diagonal entries. I want to talk a little bit more about this sign function. So we have this permutation of 1 through n, or think of it as x1 through xn. And let's look at this polynomial. This is the determinant of the Vandermonde matrix, this polynomial here. And you can apply a permutation to this formula by just permuting the xi's. So you change this where, for example, if you switched x2 and x1, you would get this, and suppose x3 went to x7 and so on. You just permute the variables like this. And what you get is another polynomial, and it's easy to see it's plus or minus the one you started with. And this plus or minus is exactly the sign of the permutation. So that's another way to compute the sign of a permutation. Act on this polynomial and see what sign comes out. So for example, let's look at the cyclic permutation. 1 goes to 2, goes to 3, goes back to 1. If you take this polynomial and apply this permutation to it, what do you get? Well, let's see. 1 goes to 2, and 2 goes to 1. Excuse me, 2 goes to 3. 1 goes to 2, 3 goes to 1, 2 goes to 3, 3 goes to 1. You get this polynomial. Now, how does this compare with the original one? Let's see. We have to look at them term by term. x2 minus x3 appears in both of them. x2 minus x1 appears here, but it has the opposite sign. And similarly, x3 minus 1 has the opposite sign. So that says that this new guy is the old guy where I changed 2 signs. And so the sign of this permutation is minus 1 squared, which is to say plus 1. So that's sometimes a convenient way to think of computing the determinant. The sign of a permutation. Okay, let's write down the big formula for the determinant of a matrix. So here's a big matrix. And what you do is you pick one entry from each row and each column. So for example, let's say we chose in the first column the third entry, and the first, and the second, and the last, like this. Now, what you do is you take the product of those corresponding entries, and you make a permutation matrix out of this choice by putting a 1 in each place that you chose. So remember, a permutation matrix is given by a 1 in each row and each column. So in this example, you would get this permutation matrix. And you take the determinant of that permutation, which is that permutation matrix, which is to say the sign of the permutation, which is plus or minus 1. And you stick that out in front of this term. And now you just add up overall choices. So the theorem is that the determinant of this matrix is the following formula. It's the sum over all such choices times the sign of the corresponding permutation times the product of the corresponding terms. So that's one version of what I call the big formula for the determinant. So let's look at this as an example. Suppose we had a 2 by 2 matrix A, B, C, D. Well, how many choices are there? Well, you can choose these two, in which case you get this permutation matrix, which has determinant 1. So you get 1 times AD. And the other choice is these two, which gives this permutation matrix, which gives you minus 1 times BC, and of course that's the usual AD minus BC. Okay, I want to make this formula more precise. The way I said it in the previous statement is slightly vague, so let's spell this out. So here's our n by n matrix. And how do you choose one entry from each row and each column? Well, you have to choose these second coordinates. That is to say, you need to choose some A1 blank and some A2 blank and some AN blank, and you just need to fill in these blanks. And so in this example I filled them in as 2, 1 through n, and these red numbers are a permutation of 1 through n, and the choices correspond exactly to the permutations of 1 through n. So the theorem in this version is the following: you sum over all permutations written this way of 1 through n, and you take the sign of the permutation and the product of the corresponding aij's. So that's a more concrete version of the big formula. So let's look at this in an example where n is equal to 3. So here are the 6 permutations of 1 through 3. 1, 2, 3, 1, 3, 2, and so on. And here are the signs of these permutations. Well, let's see, the second one I did a single swap, and in this third one it's minus, and so on. There are the signs. And so what that says is there are going to be 6 terms. And the first one, for example, is going to be a 1, 1, 2, 2, 3, 3 with a plus. And the next one is going to be 1, 1, 2, 3, 3, 2 with a minus, followed by A1, 2, A2, 1, and so on. And the last term is going to be 1, 3, 2, 2, 3, 1. So the determinant is the sum of these 6 terms with the appropriate signs. Okay, so if you look at this for a general n, it's clear that the number of terms is the number of permutations, which is n factorial, which grows very fast with n, but what are you going to do? Okay, the last formula I want to talk about is called the Cofactor Formula, and it looks like this. You write down your matrix and you pick a pair ij, and we're going to construct a corresponding ijth minor matrix. And what you do is you circle this term ij and you cross out the corresponding row and column, and you take the matrix that you get by deleting that row and column, which is an n by 1 by n by 1 matrix, indicated in blue here. And the ijth cofactor is defined to be the determinant of this matrix with this sign out front, which is minus 1 to the I plus j. And then the cofactor formula says that the determinant is the sum of these cofactors. You pick an I, and then you get AI1, CI1 plus AI2, CI2, and so on up to AIN, CIN. And this is sort of an inductive formula because it's in terms of these n minus 1 by n minus 1 matrices. So let's look at an example here for a 3 by 3 matrix. Let's take I is equal to 2. And so the first cofactor is this one here, and you get minus 1 to the 2 plus 1. And the corresponding minor is this one right here. So you get the determinant of this 2 by 2 matrix. And then you go down the column and you get this guy here, and so here you get minus 1 to the 2 plus 2 times the determinant of the blue matrix. And the final one is this guy here, and you get minus 1 to the 2 plus 3 times the determinant of this 2 by 2 matrix. And the determinant is the sum of those terms. So, for example, you get, expanding the first determinant, you get this and so on, and all the way down to the last determinant, which looks like this. So that's really just another version of the big formula, but it's organized slightly differently. And you can do it according to columns or rows, and it's clear from the way the formula is written that it's advantageous to pick a row with as many zeros as possible. That's sort of the main application of the cofactor formula, is it organizes the formula in such a way that you can take advantage of zeros. So let's look at an example like this. The second column has 2 zeros, and so the formula is going to be the 0 plus the determinant of the 2, cofactor, which is to say this matrix here, and then the other term is 0, and so there's really just a 2 by 2 determinant that you have to compute, which is -5. All right, that's a good place to stop. I will see you in class.